we will introduce electric field length in this lecture. Electric field length is also introduced by microfaraday just as electric field. It's a convenient way to help us visualize the electric field patterns. Now, electric field, as I stated in last lecture, electric field is real matter carries energy and momentum. On the contrary, electric field lengths are just imaginary. It's not a real thing that exists. It's just artist illustration to help us understand how electric field work. The field lengths are related to electric field. So at every point, the electric field, the direction of the electric field is tangent to the electric field length. And the density of electric field length would represent the strength of the electric field. Now, in this example, area A and area B had the same number of electric field lengths, which means the density of electric field length at area A is larger than area B, so which also means the electric field is stronger on surface A compared to that of surface B. If we have one point charge, the electric field goes radially outward. If we have a negative charge, the electric field length would point radially inward. If we have a pair of positive charge and negative charge, we call it dipole. That's what it looks like, and we can see electric field length start from positive charge, ends at a negative charge. Now you can also see the density of field length is much higher, closer to the positive charge or negative charge, and is smaller, much more far away from the source charge. This is a pattern of electric field length for two equally charged positive charge objects. The very interesting point here is point C. The electric field at point C is exactly zero, which means if we put any charge at the location C, the electric force on that charge would be zero. This is the electric field length for positive 2Q charge and negative Q charge. There are some rules for drawing electric field lengths. Generally, the electric field length begin on positive charge and terminate on negative charge. Unless we have unequal number of positive charge or negative charge, in such case, some electric field length could begin or end at infinitely far away. The number of lines drawn leaving a positive charge or ending on a negative charge must be proportional to the magnitude of the charge in one single drawing of electric field length. No two field lengths can cross each other. Now that's because the tangent length of electric field length represented the direction of electric field at that location. If we have two field lengths cross, then you can draw two tangent lengths, which indicates you have two different directions for electric field at that location, which is certainly not true.
Electric field lines are another way of visualizing the electric field. Field lines are continuous lines that are tangent to the field at every point in space. That is, field lines are parallel to the electric field. The concentration of the field lines in a region of space is an indication of the strength of the field. The field lines will also reflect the symmetry of the field and of the distribution of charges that produce the field. As was the case for the single positive source charge, the field resulting from a negative source charge is spherically symmetric. For the positive source charge, the field lines came out of the charge, while for the negative charge, the field lines go into the charge. In general, electric field lines will start on positive charges and end on negative charges. The net electric field due to multiple charges is the vector sum of the contributions of the individual charges. For the two positive charges shown, the field reflects the symmetry of the charge configuration. Far away from the charges, the field acts essentially like it was produced by a single charge. In this case, there is a positive charge and an equal but opposite negative charge in a configuration known as an electric dipole. The test charge illustrates the net effect when the test charge is repelled from the positive and attracted to the negative. Near the positive charge, the field is directed outward from that charge, while near the negative, the field is directed inwards. The field gets weaker much more quickly than when there was a net charge. The general rule that field lines start on positive charges and end on negative can easily be seen here. The pattern of field lines is characteristic of fields due to dipoles.